This is a continuation of last class, last session, dealing with manual sketch of Bode plot of transfer functions. I provide some more examples, simple examples. Okay. Here, this is S divided by this second order quadratic term, second order term. S is here, and this is second order term. Then this is omega naught, and this is the related with QP, right? So here, omega naught is 0.1, and QP is 5, right? This is omega naught times QP. It's 0.5, so this got to be 5, okay? Sometimes I'm mixing with Q and QP and QG, okay? So I should differentiate them, but sometimes I just mix them, okay? I hope you understand that, right? So this is QP exactly, but sometimes I call it Q. So asymptotic plot of this start from here 0 degree. So this one is this slope, okay, plus 1 slope, and this term, this line segment is looking at this 1 radian per sec, because when this is 1, that becomes 0 dB, all right? So it is like this, and during, in the middle of this, there is a double pole at 0.1 at this point. So this plus 1 slope is changed to minus 1, because this double pole brings down this slope by 2, okay? And RHP 0 brings up slope by 2. Single pole brings down slope by 1, and the single 0 brings up slope by 1, something like that, okay? So plus 1, plus 2, minus, that is very good way of writing down this, okay? So the slope has been, well, it was plus 1, and due to this double pole, slope is reduced by 2, so it is minus 2, like this, okay? And at this point, we know there is a peaking, 20 log Q. So this will be smoothly connected if Q is 1, QP is 1, but because of QP larger than 1, we have peaking of 20 QP is 20 log 5. I don't know what this number is, okay? This is 1. And the phase here is 90 degree. Why? Because the slope is plus 1. Phase here is minus 90 degree. Why? The slope is minus 1, okay? And at this peak, this is this tangential line, horizontal line. So phase here is 0, okay? So at this peak, phase becomes 0. Another example. This is what? This is integration, and this is double pole, and this is double 0, and the double pole is coming first, and the double pole comes later, and this is pole at 0, so this should come first. So initially it starts from this minus 1 slope. So this line segment is looking at this 50 radian per sec, because when this is the 50, it becomes 1, which is 0 dB. So it goes like this, okay? But there is a double pole here, so minus 1 slope is reduced by 2, so minus 3 slope, minus 3 slope, and there is a peaking, so maybe smooth connection is, I don't know. So this peaking is 20 log QP, okay? This omega naught or omega 0, okay? Let me use omega G, omega G, because there are double 0 in the numerator and double pole in the denominator. Let me use this notation. This is 100 radian per sec, and QG is 4, and QP is also 4. So this is 20 log QP is 20 log 4. I don't know. Okay. With this, it goes down, and at this frequency, at this 200 radian per sec, there is a double zero. So slope is increased by 2. So this minus 2 slope becomes minus 1 slope. And this 0 is producing this minus 1 slope and the minus 1 slope. And the 0 is producing this dipping. And size of this magnitude of dipping is also 20 log 4. Right? So you have this kind of frequency response. Yeah. How about phase? This is minus 1 slope, so phase is minus 90. This is minus 1 slope, then phase is minus 90. Okay, in between, phase is double pole, decreased, increased, but we don't care this part. Okay, but at this frequency, phase will be 0, phase will be 0. Okay, so this peaking frequency, the phase will be 0. This frequency, phase will be 0. I don't know where it is, but this phase will be 0. Okay? And this line will be connected. Okay? So they cancel actually the effect of this and this. They cancel at this higher frequency. So this line should be connected. This asymptote line is connected because of this. It has this kind of characteristics. Okay? This is very common in some case. Okay? When you are measuring something, some frequency response, you will see this a lot. Okay? You measure some frequency and some kind of this magnitude curve is appearing here, and this is another one is appearing here. Okay? So this is combination of double pole and double zero. If double pole and double zero, they are very close to each other, it generates this kind of glitch. Okay? So from this, we see the pole is coming first. This is a pole is coming first, and zero is coming later. And this dipping comes first, then zero, double zero is coming first, and later double pole is coming. Okay? So maybe you have this kind of noise somewhere. There is a pole and zero pair, closely located, double pole and double zero pair. Okay, maybe they come from the parasitic component, parasitic element of your component. So you didn't want this, and you didn't know this will happen. Okay, but it happens because of some parasitic capacitance, inductance, and resistance you ignored during your analysis and the design. Okay. All right. Okay. Now, this is a very important story. Non-minimum phase system. Okay. The system having this RHP pole or RHP 0 is called non-minimum phase system. I'll explain why people call it non-minimum phase system. Right? Just consider this. There is a pole, there is zero, there is double pole. Okay? This pole is regular pole. So this maybe we call it regular second order system. So this has some zero. Okay? Pole frequency, double pole frequency is here, and the zero is coming later. That is our assumption. So with that assumption, I sketched this pole. By the way, this is generated with the exact computer simulation for this particular case. So this QP is here. So the peaking 20 log P, 20 log QP appears here, and omega naught is here, and it slows down with this minus 1 slope, and there is a 0, and the slope is increased by 1, so minus 2 slope rolls down with minus 1 slope after this frequency. Okay. So how about phase? Here phase is 0, phase is 0, right? Because this is a constant line. And with this phase is decreasing by 180 degree. Because of the Q is large, because we have high peaking, we assume, we know the Q is very large, then phase is changing very abruptly, and it goes down to this minus 180, okay? And this 0 is somewhere here, and 0 is here, and 0 eventually 0 boost phase by 90 degree, so it goes like this, okay? If the corner frequency are far from each other, then phase of this gonna be minus 135 degree, and the phase at this frequency, at double pole frequency, should be exactly not 0. Oh, 0, right? No. Because this is a different case. Okay. Maybe there is some exception. Okay, I said when this peaking occurs, the phase is 0 degree, but this is different. This is due to this second order peaking, so phase here is should be minus 90 degree. Okay, something like this. This is a regular system, and non-minimum phase system. We have this. This is what? This is RHP0. So this is a magnitude sketch. Magnitude remains the same because this RHP0 is the same as the regular 0 when magnitude is considered only. Okay, but phase is different. So beginning part will be the same, but this is pole. So eventually phase is decreasing by 90 degrees. So it ends at this minus 270. Okay, so at this frequency, at this 0 frequency, phase is minus 225 if the corner frequencies are far apart. Okay, they are widely separate. This might be true. So this is the phase start from 0. It ends at minus 270. Okay. Why this is called the non-minimum phase system? This system phase variation is 180 degree. In this term, phase variation is 270 degree. So phase variation is non-minimum. So people call it non-minimum phase system. Very strange name. But this means there is a RHP4 or RHP0 in the transfer function. There is the non-minimum phase system. Then this is the minimum phase system. They don't call it, there is no term minimum phase system, just regular system or a system. Okay? This is very important. Actually, this is the duty ratio to output transfer function of many PWM converters, boost converter, buck boost converter, shook converter, and all the variation from 3 converters, isolated version, by inserting some transformer. So the converter you will be dealing with is probably this non-minimum phase system. And this characteristic is bothering us. This phase is, in the regular system, final phase is minus 90 degree, but in this non-minimum phase system, final phase is minus 270 degree. This is very bad. In control design, very bad. In stability assessment, and very bad to stabilize this one, and also bad to optimize the closure performance of this PWM converter. Okay, so this was some problem in the past, and they developed the control scheme which provide the reasonable performance at the presence of this RHP0, okay, for the non-minimum phase system. Okay. We stop here and take 2-minute break and finish the remaining part of this lecture. Okay? Take Okay, let's continue what we are doing. So we discussed the Bode plot of transfer function with some examples, and we focused on the implication and the meaning of that. Okay, so that is one thing. For the given transfer function, you need the sketch, not plot, just the sketch, hand sketch, asymptote of all the plots, and use that result to analyze something. Many cases, you need to manipulate a transfer function. You need to divide two transfer functions, and you need to multiply two transfer functions. Then you plot each of transfer function, asymptotic plot, and if you are multiplying two transfer functions, then you add the magnitude curve. If you divide two transfer functions, then you subtract the asymptotic plot of two transfer functions. That is the way of doing some algebra using asymptote. Okay, so this Bode plot technique is very useful, but the least useful part of it is just sketching the Bode plot of transfer function. That is the least significant aspect of that. But most students, they are trying to do that, and if they know how to draw the Bode plot or to simulate, they assume they know they finished learning the Bode plot. That is not the case at all. Okay, during doing some manipulation of transfer functions, you will be using the asymptotic plot of each of transfer functions, and you add them together and divide them together, and you multiply them together. Everything can be done, this asymptotic plot, graphically, without any calculation or any algebraic manipulation. Okay, that is the more useful, more high-level application of this Bode plot. And during that process, some need will arise. Suppose you have this kind of asymptotic plot, and from this plot, you need extract the transfer function of this, which corresponds to this asymptotic plot. There is the reverse process of sketching asymptotic plot, but this reverse process much more useful than this forward direction of just plotting the asymptotic plot. Okay, that is frequently used from the analysis of this feedback system, or in designing the controller of your feedback controller. Compensation of your feedback controller. Actually, one famous technique of this controller design is loop gain shaping technique. You will learn the loop gain. Loop gain is most important quantity in any dynamic system. By shaping the loop gain to the desired form, you can obtain the desired closed performance. For that, you need to use this graphical approach. Okay, you will be learning that approach a lot. Okay, that approach is part of design-oriented analysis, DOA, advocated by Dr. Middlebrook. I call him the father of power electronics. Okay, for the last time, he died maybe 10 years ago, and the final stage of his life, he was concentrating on this DOA, design-oriented analysis, and he was writing some book about that, but he couldn't finish it, so that book is not published. The analysis and the design approach I'll teach you here is very close to that approach, design-oriented analysis. Okay, so one important segment of ingredient of that approach is this one. Okay, constructing this transfer function for the given asymptotic plot. This is a very simple example. Later on, you will be learning some complicated practical cases of this. Suppose you have this kind of asymptotic plot, then you can immediately write down this equation. So start from the low frequency. So it has this one. So you have this differentiation and with some gain. Okay, that gain is determined in many ways. Okay, first leave this the unknown parameters, and you have a pole here. So omega p1 is coming here, and so slope is changed from +1 to 0, and you have another pole here. So slope is reduced to -1, and you have 0. Okay, then 0 is coming here. Okay, so with this, you know this frequency, this frequency from these three frequencies, this determined from this slope, this S is determined, and the remaining question is this one, how to determine the K. Suppose this value is known, this peak value is 20 log Km, as given by, or you measured, okay? Then at this point, you just consider this term. As I said, you are interested in the frequency below this point, you don't care this, okay? You just take a look at this, and you evaluate this term at this frequency. That value is Km, 20 log Km, all right? So leading coefficient of, this is the equation we extract as I explained just before, and this Kd is at this frequency, magnitude is Km, so this is the equation, and this is the linear equation, and the Kd is determined like this, okay? So this will be used for many purposes, all right? Suppose you have some measured something, and frequency, let's suppose, looks like this. I don't know. Looks like this, okay? So frequency response is not this line segment or this cornered one, but this smooth curve. Then you assume this is the asymptote. This is asymptote. From that approach, you can evaluate this. From the peak value, you evaluate this, and you plot this one, and compare with the exact one. They are very similar, okay? That is the one most simplest case of system identification. From the frequency response, you predict the transfer function of the system. That is the primitive example of system identification. There are many ways of identifying the transfer function from the input-output measurement. This is one very simple example. The very basic approach. Okay, so they can be used like that. Another example. Okay, so same asymptotic plot, but now this high frequency value is known. Okay, this is unknown. All right. So, but there are many ways of calculating this. This transfer function will be the same. The thing is to determine the value of the K, this leading coefficient of this differentiation. Okay, when S goes to infinity, everything goes to infinity, then you take just the coefficient of this. So this is the magnitude evaluate at the infinity at this frequency, which is the same as this. So this one should be same as this, which is this. So Kd is determined in this manner. There are many ways of doing this. Okay, you don't need a plot. You don't need to manipulate the system block. Okay, some case for many cases, and the DOA is to eliminate the calculation or manipulation of this block. Just to use this graphical approach. And asymptotic approach to get all the information required for the control design and performance evaluation. Okay, so we'll cover that later. Most of stuff coming in the later is based on this kind of approach, Bode plot, asymptotic Bode plot, and this design-oriented analysis, which is very useful. Okay. I think we covered this, but somehow we briefly review this. Okay. So this is about the inverting amplifier with operational voltage amplifier. So this is the compensation design. Okay. So in the previous time, this triangle was directed in this manner. So now I switch the position. I rotate it 180 degree. So this is the input and this is output. Okay. So when this current, DC current is coming in, then this current is coming in, and going out this direction, and usually it comes out from the bias voltage of the OP-amp, right? So for this amplifier is non-inverting, this is inverting amplifier because this input is connected. It's inverting terminal, and KCL at this inverting node is given by this. Then input output equation is this. Okay, so GS is transfer function of this block, usually called compensation, and the ratio of impedance G2S and G1S with negative sign in front of it. You know this, okay? And the zero frequency is, there are two conditions for zero. To make zero, at particular frequency, this becomes zero because it comes here. And at particular frequency, this becomes infinity because it comes here. This is infinity, then this is zero. Then means whatever occurs here, output becomes zero. Okay? And pole frequency. So when this is infinity, G2 is at infinity at particular frequency, and that is the pole, because without any input, output will be generated. Or if this one becomes zero, that also becomes pole because it comes in the denominator. Okay? We discussed this before. Okay? So the structure of this is usually, for our purpose, we need this. We need this term. Because of the DC regulation, we want to have ideal voltage source or very close to the ideal voltage source. Then output should be remain at the desired value. So for that, we need this integration, and there are a bunch of poles and zeros. Okay, it comes just the poles and zero, double pole, double zero, single pole, single zero, and the combination of them. Why we not using the double pole or double zero? It is very impossible. It is very difficult or almost impossible to put the pole and double zero. Sometimes we place this pole and zero to cancel something. Okay. At that case, if they are exactly matches, the cancellation will be like this. Okay. If there is some mismatch, result will be something similar to this. This is the location of the cancellation. Okay. This is some you need some imagination, right? I'm using some analogy here. Okay. But if you try to cancel double pole with double zero, that will be impossible because a slight mismatch will produce what? I said that. This one or this one. Okay? Because double pole and double zero pair, if they are perfectly at the same location with the same Q, then they'll cancel perfectly. But that is impossible. Any slight mismatch will produce this, okay? For this case, single pole, single zero. This might be not possible, but this is okay. This is still okay. Okay? That are all the same. But this is entirely different. So they don't use, and nobody use the second order function in the compensation. Right? So that is for this reason. Okay, then we have this structure. You already know this. This create at zero here, and this combination create zero here. But that is the pole because it comes in the denominator. You create pole, and for this case with the three circuit component, this will create zero, and these three elements combined here will generate pole, and the same is true for this case. This will generate a zero, and this combination of these three components will produce pole here. Okay, so knowing this is very convenient to design something, compensation design. Okay, without this you need the trial and error, or you should go back to the table to take a look at. For example, this is one simple example. So DC current, we need DC current pass for the integration function. So IDC is passing through this. Oh, no, the other way around. IDC is passing through this. And the one part of that goes here, the other part goes like this, and this is coming out like this, okay? So at DC, when frequency becomes 0, so this is infinity, so this is nothing. So we have two current paths, C2 parallel and C3, and one current path, okay? It should go this direction. It cannot go into this ideal op-amp. So this is integration. So we have this and this integration gain. And from here, we have pole. We have 0. And through this component, we have pole. This becomes 0. This becomes pole, right? Because this is the G2. Okay. Then transfer function is we have this and we have pole 0. It's this. Okay. This is called two-pole 1-0 compensation. There are two-pole 1-0 compensation. Some people say this is a type 1 compensation. Some strange people, they say type 1. And the previous one, you have 3-pole 2-0. That is called the type 2. Then they have type 1. No 0. That is what? Integration. Okay? Type 0 is just integration. Okay? So they are using this term. Okay? Very strange name. Okay? That they are referring the number of zeros. Number of 0 is 0 here. Number of 0 is 1. Number of 0 is 2. Maybe type 3 has 3 zeros and 3 or more poles. Very stupid name, all right? But you should know they use this one, type 1, type 2. Some guy, they use type 0. Okay, this is the, let me give you this final example. And this is integration, compensation structure we went through. Okay, so this is type 0. And because transfer function is this, and this met this condition, okay, G2, this is G2, evaluate DC is infinity, G1, evaluate DC is something other than infinity, okay, then this becomes infinity. This is type 0. And this is the compensation. I mentioned the topic 2. Okay, when talking about the feedback control of buck converter, we use this structure, and due to the same, with the same knowledge, you can write down this equation easily. Okay, and of course this also met this condition because you have this capacitor. So DC value, impedance of this parallel combination infinity, and the DC value is opened. This R2 is finite. So we have this requirement satisfied for this case. Okay. So this is end of section among the frequency response of dynamic system. What we have discussed so far is for the linear time invariant system, and from the next lecture we'll be discussing frequency response of PWM converter, because the PWM converter is not linear time invariant system. Okay, so the implication of this and how to adapt the previous knowledge or adopt the previous knowledge to the PWM converter. And what is the implication, what is the benefit, and what are the limitations of that approach will be discussed starting from this lunch day. All right? Okay, we'll stop here. Okay, thank you for your attention and have a good day.